Hello, everyone. I'm Pablo Castellanos, and today I want to share with you my work on provably correct generation of constraints for the Plonk zero-knowledge protocol. So first of all, let me say what even is the Plonk zero-knowledge protocol. So it is an example, of course, of a zero-knowledge protocol, which is a cryptographic tool that allows me to convince someone else that I know some private piece of information, but without actually revealing what this information is. Now, this is usually expressed in a statement like, I know an input to some function that results in some particular output value, but I won't say the input value. And one example is I could prove to someone that I know some input value to this function that results in the value true. Now, the good thing is that there are already some implementations of protocols like Plonk itself that solve this in a very general setting, so for any MP computations. Now, the bad news is that these protocols require that the computations are described in a very specific way using algebraic equations. In the particular case of Plonk, these equations have to be of this exact form, but it may vary depending on the protocol. And well, going back to this function that I mentioned before, this could be a graphical representation of a graphical description of this function, which, as you can see, it's somewhat intuitive and easy to understand. But of course, this is only a graphical representation. The actual description that is needed by the protocol is something like this, which, of course, is completely opaque. You have no idea what this is doing. And of course, it's very easy to make a mistake when writing something like this. So this is where my work comes in. In the past few months, I have been working on Blink, which is a declarative domain-specific language that allows you to describe these computations in a higher-level way more easily, and then to compile them into the actual constraint system that is needed by the underlying zero-knowledge protocol. Also, as far as I know, this is the first such language to target the equation, the style of equations in Plonk, even though it's a protocol that is getting more and more popular by the day. Now, if we look back to this box in the bottom, we can see an example of a program in Blink describing this same function as before. And you may notice that this syntax is very similar to Haskell syntax, and this is not a coincidence. This is because this language has been implemented as an embedded DSL in Haskell, which is, of course, very convenient for a lot of reasons, but mainly it means for us that we can use liquid Haskell to prove properties about our implementation. And one particular property that I was very interested in is proving the correctness of this compiler function. And this is because any system of equations that is either over or under constraint can compromise the security of the underlying protocol. In particular, a system of equations that is missing some equations can allow a malicious user to give a convincing proof of a false statement. So, of course, this is a very big issue. Now, the way that I solved this is I started by defining the formal semantics of Blink compositionally as a Haskell value, and then I used liquid Haskell to prove that the compiler actually preserves these semantics. To be a bit more precise, the exact theorem I proved is this. So for each Blink program, every evaluation of the variables that appear in the program satisfies the elaborated version of the program if and only if it is a solution to the constraint system that we get as a result of the compilation process. Now, what do I mean by this elaborated version of the program? If we look back to the left, we see a multiplication expression, for example, which gets elaborated into this arithmetic circuit in the middle. As you can see, every intermediate value gets labeled with some variable, and this variable is going to be referred to in the system of equations that is the result of the compilation process. So this valuation satisfies this if, well, the value assigned to this variable is going to be, in this case, the multiplication of the values in the two other variables. And well, just to recap, my work has been designing a domain-specific language called Blink for describing this kind of computations in a higher-level way, and a compiler to generate constraints for a very popular zero-knowledge protocol. And moreover, I managed to use liquid Haskell to prove that this compiler is correct in that it preserves the semantics of the program. Thank you very much.
Hello, everyone. My name is Sarah. Okay. And I recently started a PhD on the topic of usability of interactive theorem provers, which, for example, Agda call clean. They are notoriously famous for having a very steep learning curve. And with this starting project, our intention was to figure out what obstacles novices actually face when they are learning to use an interactive theorem prover. So to be able to achieve this, we actually got a hold of 35 bachelor students at the end of their functional programming course, where they learned some basics of Haskell, and then they had an introduction to Agda. And after they did their exercises, we gave them an online survey where we asked them to list up to 5 obstacles that they encountered when learning to use Agda. So we actually kept it at open-ended questions because we didn't want to give them examples and see what they react to. We really wanted to hear from them what the obstacles were that they faced. So you can see that these are free text fields. So I actually had to use qualitative research techniques to be able to analyze this data. I don't have time to go into detail about all of this. You can come to my full-length talk at Tidy if you're interested. But I would like to dive into the idea of coding, which is a very important aspect of this analysis. So it is basically the idea that you label or code the different data that you get. So for example, when they referred to Unicode, we coded it as syntax. When they referred to the plugin failing, we coded it as tooling. But I would like to point out that consider this second phrase, which is about syntax highlighting disappearing when the code actually doesn't compile, which is also labeled as tooling, right? But these two, they don't really refer to the same thing. So to be able to grasp these nuances, we actually added subcodes, explaining that the first one is related to tooling, but to unintended behavior. And the second one is related to tooling, but to impractical design. So from this analysis, we actually were able to determine 5 different obstacles, which I will sort of skip over during this presentation, because I would like to use the opportunity to tell you about some observations we can make about Agda from these obstacles. And I will be illustrating it on this beautiful example of my own code that I learned when I was learning to use Agda, which generates this wonderfully short error message when compiled. So the first thing we can observe from our obstacles is that many of them are a result of the high coupling between Agda's underlying theory and its design. So imagine you get this code as a beginner, and okay, you think to yourself, what's the first thing I do? I attempt to understand the message. But if you look closely, there's a lot of terms that someone new is like, what? Scope checking, operators, grammar? None, I'm very confused. So you can see that there is this link between the theory and the design. The second point is that Agda's ecosystem has very little supporting infrastructure for novices. So in this example, after we fail to understand the message, we ask the internet. Unfortunately, it actually yields no useful results if you copy-paste this error message into your browser. And you can also see that whenever you Google something about Agda, you get very complicated examples, which a novice will have a lot of trouble trying to decompose into what they actually need. And finally, the third observation we can make is that Agda's design makes it dependent on a custom and not so user-friendly development environment. So what we can see here, after the message has failed us, after the internet has failed us, we attempt to stare at the code to figure out what's wrong. But actually, unfortunately, we realize that because our code doesn't compile, the syntax highlighting is suddenly gone, which makes this task so much more difficult. And Agda is quite difficult to write without an editor, so we have to use one, but at the same time, it has these strange design things that are not quite what we would want them to be. And what we can see from these 3 observations, I think, is that oh, yes, this was the error, by the way. There's a space missing. But what we can see from these observations is that it seems like we need to find a way to make the infrastructure for novices more sturdy and more accessible. Thank you.
Going to tell us about contract calculus.
All right. Thank you, everyone. So here, my research is about providing a uniform foundation for contracts and try to capture all contract calculi in the literature, provide a way to prove meta theories that are reusable. The contracts are a lightweight behavioral specifications that is done by dynamic checks. For example, the one colored brown is a contract stating a function takes even numbers and return odd numbers. In practice, it will be checked by using dynamic checks that checks the contracts are actually satisfied. For example, the proxy colored blue is a wrapper function that will intercept functioning applications and then insert appropriate dynamic checks. In practice, people have added a lot more interesting features on top of this. For example, in Crystal Stimulus work, they added a blame labels, the one colored blue, that is used to report which contract has failed during runtime. They have also added the bar colored brown to delimit expressions and to associate each delimited pieces with a source file with a hope to help user point to the error to the file that contains the error for bug fixing. In my work, I present a uniform annotation to encapsulate both features and beyond. For example, the one colored brown, the source file annotations, and the one colored blue, the contracts. They are all implemented as annotations on the wrapper functions, and they are all uniformly presented as a pair. So here comes the ground for meta-theory reuse. There are two steps to finish the meta-theory reuse. One is to provide a way to prove meta-theories, to prove properties by using transition systems homomorphisms. The second is to reuse meta-theory by combining transition systems. So the first step of my work is to view the reduction sequence as a transition system. And then I could prove specific properties about the contract calculus by establishing the homomorphism in red. For example, I map the reduction sequence on the left as a transition system through the homomorphism to the transition system on the right, which contains exactly two states, OK and error, the state which can transition from OK to error, but never back again. Therefore, the existence of the map in red tells me that the reduction sequence will transit from an OK state to error, but never got resetted back to OK, which is a sanity check for contracts. Of course, recall that we have provided a uniform representation for all contract features and variations. So we can decompose the contracts into pieces, like the one which contains only the brown annotations and the one which only contains the blue annotations. This way, we could decompose the transition system on the right, which is the transition system for both annotations, and project the annotations, project the state, into two separate transition systems in the middle. And then, for the projection on the top, we can reuse the map H checking, which is colored red, to tell us that the combined reduction sequence also only reduced from OK state to error state, but never back again. I have applied the same technique to capture more than just blame tracking, but also space-efficient contracts, which is a way to remove duplicate checks to improve performance. And I have used the same technique to prove that space-efficient contracts are equivalent to the original contract systems. Thank you.
Hi everyone, I'm Nick Hill. I'm going to be talking about Seedser, which is an improved way to fuzz deep learning compilers. So what is a deep learning compiler? I'm sure most of you guys are familiar with a normal compiler. It takes in a program and it gives you optimized code, kind of oversimplified. But a deep learning compiler is the same thing, except instead of taking in a program, it takes in a machine learning model. Now, how can we best use fuzzing to find bugs in these deep learning compilers? So on a normal compiler, if we're trying to fuzz it, we can do something like this, where we have some sort of program generator, and we take the compiled input and we give it to an oracle to see if the output of the compiler kind of resembles the correctness given by the input program. And in this program generator, we have this idea of kind of correct syntax, correct semantics, type checking that we might want our input programs to have. And for a deep learning compiler, we have the same idea, except we generate machine learning models instead of full programs. And again, we have this notion of correctness in terms of if a machine learning model is correct in terms of its parameters. So one deep learning compiler I'm going to be talking about debugging is called TVM. It's an open source one. And similar to a normal compiler, it has a lot of different stages that kind of reduce in complexity over time. towards some sort of target IR, in this case LLVM. And there's a lot of different literature on kind of fuzzing this already. One of these is called NN-Smith. This works at kind of the highest level, so generating these machine learning models at the very top level, something you would get directly out of TensorFlow or PyTorch. But the issue here is that like hundreds of these operators that TVM uses are exclusive to the low level. This is like trying to debug LLVM, but you can only generate like 1,000 line C programs to debug it. So let's try a different approach. Instead, let's start at this low level and just mutate things that we already have in the low level. That's what teaser does. And we start with the seed pool of kind of common intermediate representations that are already lowered, and we kind of run mutations and different optimizations on them to ensure that they remain correct. But the issue here is that the only high-level properties we're encoding are the ones that we initially have in our seed pool, which again is hard-coded. So this is like trying to fuzz LLVM, but you can only mutate like 3 C programs that I give you. So Seedser kind of fills in this gap. So essentially, it takes in the NN-Smith model output, which has a lot of diverse neural networks, and allows the user to prioritize different high-level properties by encoding their own heuristics. Let's say I just updated part of teaser that has to do with convolutional neural networks, so I want to test those deeper. It allows you to prioritize those. It also tests teaser's ability to load things from a file. This is a very common capability that teaser as a deep learning compiler has. You should be able to load a neural network from a file and then compile it down. But neither of the previous 2 works actually encounter that because they all have the models in the code already. So we'll see that the performance for Seedser, which are the 4 colored bars here, I've just kind of selected 4 arbitrary heuristics that have to do with convolutional neural networks. They actually outperform the default seeding for teaser, which is shown in the black dotted line. But more than coverage, what's important is that we're finding bugs. So some bugs that we found here have to do with type mismatches, things that have to do with loading in PyTorch models, things like that. And we'll see that actually a lot of these bugs that we've discovered have already been reported and are on GitHub in open issues or on the TVM page. So some main takeaways is that seeding, of course, can improve your fuzzing direction, both in deep learning compilers and in normal compilers. Again, we found bugs in the model loader rather than just the compiler itself, which is something that the previous 2 works didn't do. And I think there's a lot of takeaways here that we can take when you're debugging normal compilers as well, not just deep learning ones. Thank you.
Thank you, and this is...
Next, Daniel will tell us about spreadsheets.
So, hi, my name is Daniel, and I'm about to talk about the first step towards an operational semantics for a generalized spreadsheet core. So, spreadsheets are one of the most used paradigms in the world. They are many people's first introduction to computing. They are used in finance, they are used in analysis, they are used for programmers and non-programmers and the like. And this year, we are actually celebrating their 55th anniversary. And the current state of the art is we would really like to have like these 3 characteristics. We would like to have orthogonal extensions like lambda functions, nested structures, nested arrays, and the like. We would really like to have a self-contained language because having to marshal or learn a whole different language in order to do, for example, macros, it's really inconvenient, and it would be really nice to have some sort of formal semantics to it, so we can analyze the programs and macros that we actually write. So Excel and VisiCalc actually offers orthogonal and formal semantics. BISSH offers orthogonal extensions and self-contained in a self-contained language, which is a scheme. And we don't really have any examples about a language that offers formal semantics and self-contained in a self-contained language. Nevertheless, the Sensheit project offers the Lily language, which is a computing reactive language, which offers UI as a function of the model. It offers orthogonal extensions such as lambda functions, it offers nested structures, it offers gradual typing, and the current work takes the Lily language and offers a formalization for a subset of it, which is called the Silly language. So how do we make a Turing-complete spreadsheet? Well, we take classical lambda calculus. We add a little bit of quotation, which freezes expressions. And whenever you have quotation, you have to add also splicing. You add a little bit of variables and mutation here and there. And finally, when you add array support, you have not only a functional spreadsheet, but so much more. Something that allows you to do symbolic computation and the like. So some context, you're going to have three contexts, some context from variables to types, variables to memory locations, and finally store from locations to expressions. And this is the kind of productions that we'll be working with. A really important thing is the down arrow operator, which we will call the evaluator operator or the big step operator, because it's really important for quotation. So you can quote any expression that you like, and when you splice or evaluate a quoted expression, you do not only get the original expression, but you also get the closure. So you are guaranteed to not add in any symbols or scope issues. Every quoted expression also has a lazy type, which is the typing judgment that you see above. And this means that evaluations can change the type of an expression, which is a really unique language feature. So you can also have variable reassignment in the usual way that you would expect it. You just replace things. These are some of the productions. You also have a sequence expressions. This is pretty much like the state monad semantics. And we can finally have some code. So in this code, we show how we assign x and y to 5 and 1. And then we quote the expression x times 2 plus y, which saves the abstract syntax tree into the variable lx. Now, if we evaluate lx, notice that we pull the current values of x and y. But if we reassign and it's on y, we pull the new values with the current scope, of course. So with just quotation and reassignment, we get for absolutely free reactive behavior, which is absolutely amazing. Here's another example. It's a little bit more simple, but it has these steps. Now, arrays. In Silly, which is the subset of Lily that we will formalize, we can only model spreadsheets by charge encoding arrays. Nevertheless, we could also provide this new production that it basically says that the evaluation of an array is the evaluation of the terms. This is just an example of how a spreadsheet would look like in code. And you could totally take this code and expose it in the UI, since the UI is a function of the model. Notice how if you change the dependencies of any of these cells, you get a different result at the end. This is actually very close to lambda calculus, whatever you know. And thank you very much for your time.
We've saved the best for last. Iona will tell us about we get the video. Here we go. Verified equivalence checking for regular expressions.
Okay, hello. So I will tell you about an equivalent checker for omega regular expressions, but let me first start with some motivation why we want that. So languages over infinite words are in general a nice formalization. For example, we can use them to model the behavior of reactive systems. So let's take an example. Let's take a coffee machine, and it has a behavior that is modeled with this automaton here. And now we want to verify the coffee machine, so look that it's actually doing what we want. So we have a specification what it should do in the system. And so we abstract the system and the specification both as a language over infinite words, and then check if the system matches the specification. This means that we use this verification problem to just a language equivalence or inclusion problem, and in general, many problems can be reduced to language equivalence or inclusion. In general, we also want that our equivalent checkers are trustworthy or verified in general, because we all know coffee machines are important. And so let's look at some representations about languages over infinite words. So there are automata, the omega regular expression, and logics. And in general, like automata and logics were studied already a lot and are also verified in proof assistance, but omega regular expressions not. And yeah, this is although they have a lot of advantages. For example, they are syntactic objects and they are easier to reason about, especially in a proof assistant. And this is why the goal of this project is to write a verified equivalence checker for omega regular expressions. But now let's look what are omega regular expressions. So they're quite similar to regular expression, but instead in the last case of the star, we have the omega operator, which means that we have an infinite repetition of some finite word, which means we only deal with infinite words here. So omega regular expressions describe only infinite words. And now that we have this, we can write an equivalence checker. And the idea of the equivalence checker builds on the notion of derivatives that was developed by Brzezowski. And so the derivative of a language is always in respect to a symbol a, and so it's all the words that if you put the a in front of it, that the original word was in the language. And now the key theorem our equivalence builds on is that two languages are equivalent if and only if all of the derivatives are equivalent. And with this idea in mind, we develop an algorithm. And so we start with our two initial expressions, and then we compute the derivatives of them, until we either reach only trivial equalities, so just pairs of expressions where we immediately can see that they are definitely describing the same language, or we find some kind of counter stop and then can stop. And this is written down with these rules on the right. And then we can use these rules to write an executable algorithm, which means that deterministically applies these rules. Also, derivatives have the nice property that you can compute the derivatives directly on the omega regular expressions, so you don't need the languages. And to detect these derivative equalities and also the counter sub, we use some syntactic criteria. And with this algorithm, we can then prove its soundness. So this means if we start with the two initial expressions and end with the empty set, then we can conclude that the languages are equivalent. And if we find a counterexample, then we can conclude they're not equivalent. Unfortunately, as a note, this algorithm is not complete. And then we formalized all of this in the proof assistant cog. We wrote algorithm there and verified its correctness. And in the end, we extracted the algorithm to an OCaml program, wrote also a nice parser around it, so that in the end, you can just give it the two expressions, and then it computes to you if they're equivalent or not. So to conclude, we formalized omega regular expressions in the proof assistant cog. Then we developed and also verified an executable equivalence checker on them. Yes, and maybe a relative obvious future work would be to manipulate the algorithm that we can reach completeness. Thank you.